All right, folks, welcome to this new format where we're going to do video lectures during this epidemic that we're facing until the rest of the semester. Now I'm going to use slides with my big face in the corner of the screen. Hopefully, hopefully that's going to work quite well. Let's hope for the better. Uh, Now, today we're going to touch on a topic that is perhaps a little bit more challenging still than what we have done before, but uh, I would hope that you will still manage to understand all of it. And in any case, it is important stuff to understand that in order to get to more important concepts in mathematics, like the concept of function. Uh, Now, I've been playing a lot this week with models to try to understand where this epidemic is going. And I just want to show you a little something where is it? Image. Where's my image? My image is supposed to be there somewhere, but it's not showing up. Where is it? Okay, I've got it. Yeah, so I've been playing a little bit. I've got numbers for Canada and the US to try to figure out where this pandemic is going, and it's not looking too good. Um, as you know, in the US, there's now more than 50,000 reported cases of COVID-19. Uh, about 800 people who have died, but this is even worse than that because those are just the reported cases. If you're trying to understand how bad that is, you have to try to use models in order to understand what is the actual number of people who are currently infected with that disease. And based on my estimate, that might be as many as 3.4 million people, which means that we're nowhere near the end of that. If all those people were to die at a standard death rate, that would mean just with the number of people who are already infected, that 41,000 people would die just in the US. And yet people there don't seem to be doing much about that. So I'm just mentioning that because, of course, in order to get good with modeling like that, you need to understand some concepts like the concept of function. And in order to be able to do that, guess what? You need to understand some elements of set theory. So this is what we're going to look at today, trying to figure out an important concept that is eventually going to lead us there. So let's move that aside and move to our slideshow presentation for today. So I'm going to change my window here. Okay. And we're going to be talking about the power set. I call this lecture the true power of set theory. And we're going to look at one particular axiom, which is the power set axiom, as well as its, I said consequence on the slide, but of course it should be consequences. So let's look at that. We've already discussed a number of fundamental axioms for set theory, and as I said earlier, what we're looking at is what's called Zermelo-Fraenkel set theory, which is the most widespread way of doing set theory. And we started by looking at three fairly basic but very important axioms. The first one was just the non-vacuity axiom that tells us that there's going to be at least one set that exists in our universe of discourse, right? That which we're trying to describe using Zermelo-Fraenkel set theory. The second axiom was also very fundamental, very basic, which is the axiom of extensionality. And that axiom is basically telling us when sets are identical with each other. Now, on that basis, we proved a number of basic properties of the identity of sets, namely that it's reflexive, transitive, and symmetric. It also allowed us to define the notion of a subset and the notion of a proper subset, and we've also examined the properties of those. the notion of subset is, of course, the most important one, and we saw that the subset relation is reflexive, it's transitive, and also anti-symmetric, which gave rise to a really important and interesting way of showing when two sets are identical with each other. And the third axiom is the axiom of separation, which in modern set theory replaces the old principle of comprehension that was used in the early days of set theory. But of course, that principle of comprehension, as we saw, is inconsistent in that it gives rise to paradoxes like Russell's paradox. Okay. So the axiom of separation, on the other hand, is perfectly safe, perfectly good, and it allows us to take one set and a property and form a subset of the set that we are given using the predicate in question, which expresses a property, so that we can form the subset of the set, which is the subset of objects that satisfy a certain property. Now, those were the three basic axioms, and then we turned our attention to other axioms that allow us to form bigger sets. Right? We start from some sets that are given, and we make set constructions that result in bigger sets. Now, we looked at two of those. First, we looked at the pairing axiom that takes two sets and allows us to form a set that contains those two sets. But in general, we can think of it as forming collections of sets that are already given. And one particular case of that, of course, was the singleton that we could form where both elements of the pair are the same. And then we looked at the union set axiom, which allowed us to take a collection of sets and to form a new set that contains the element of each set in the collection. Now, that in itself allowed us to define the binary union, which is the union between two sets, the intersection between two sets, the difference between two sets, that also allowed us to form the relative complement of a set, as well as the arbitrary intersection of a collection of sets. Namely, we take a collection of sets and then we form a new set whose members are those elements that are in every single set in the collection. So that's where we are at this point. Now we're going to turn our attention to a third axiom, which is a little bit like the first two, in that it takes a set or a collection and allows us to form even bigger sets. In fact, they're going to be even bigger than the ones that we have looked at when discussing the pairing and the union set axiom. So that's the power set axiom, an extremely powerful set indeed. As I wrote on the slide, clue is in the name. So what is this power set? Good question. I'm glad you asked. Well, since it's a philosophy class, let's start with the question, what truly is power? Because if we want to formulate an axiom about the power set, we are looking for a first principle. And to know true first principles of power, one must know what power truly is. Now, as is often the case in philosophy, there's not much of a better place to start than with Plato. In fact, Plato said, the measure of a man is what he does with power. Let's think about that for a second. What do you think he means when he says that? What did he mean? Well, to truly understand what Plato means, we're going to have to learn some ancient Greeks, because that's where wisdom truly lies. So this is why it's so common to do that in philosophy. So let's look at that. No, I'm kidding. Of course, we're not going to do that. That's not the kind of philosophy that we are engaging in here. We're doing foundations of mathematics. All right, so the power set axiom is just this one sentence, which we take as primitive in set theory, that allows us to form a new set, given that we are given a set that contains some subset. So let's just put it down soon, but first we're going to look at some examples. So let's take Let's start with the simplest set of all, the empty set. What are the subsets of this set? Well, as we saw last time, the subset, the empty set is a subset of itself. That's a vacuous truth, right? Uh, and nothing else, in fact, is a subset of the empty set precisely because it has no members whatsoever. So the set containing all the subsets of the empty set is just the singleton containing the empty set, right? So this is the one subset that the empty set has. So the set containing all the subsets is just that singleton. Now that might be a little bit puzzling. So let's look at other examples. Suppose we take the second simplest set that we can think of, namely a singleton. So here I have the set A, and it's just this one set that contains small a, an object or a set, something else, right? Now, what are the subsets of this set? Well, there's two of them. The empty set, which is a subset of everything, right? So the subset is always going to, the empty set is always going to be one of the subsets that we have to look at. But furthermore, since the subset relation is reflexive, that means that A is also a subset of itself. And there's going to be nothing else. So that leaves us in a situation where if we want to form the set of all the subsets of A, we have a pair where the first member is the empty set and the second is A itself. Or if you prefer, you can write A as it is defined, namely the singleton of small a. All right, so that's our second example of forming a set of subsets. Let's keep going. Suppose we take now a pair, a set which is the next simplest case, namely a pair, a set that contains two objects. Here, the two objects are small a and small b. What are the subsets of this set? Well, as always, the empty set is a subset and A itself is a subset. But here we have two additional subsets, namely singleton A. If we look at singleton A, of course, every single one of its members, there's only one, is a member of A, which contains, well, small a as well. Same thing for the second singleton set, which contains only B, because B is, of course, a member of A, so singleton B is a subset of A. And nothing else is a subset of A. So now we're going to form the set of all the subsets of A, and that's going to contain four elements. As always, we have the empty set and A itself, but now we have the two singletons on top of that. And as always, instead of writing A, you can write it the way it is defined for this example. Okay. Is that good? I hope it is. So let's look at yet another example. Next simplest example, a set that contains three objects. Well, first we're going to look at all the subsets of A that contain zero members. That's going to become a sort of way of thinking about sets of subsets. All the subsets that contain zero members, well, there's just one, that's the empty set. Good. Now, all the subsets that contain one members, that's singleton A, which is a subset of A, singleton B, and singleton C. When we write three sets like that, separated by comma, followed by subset, that's to say those three things are subsets of A. Then we have the subsets of A that contain two elements, namely the pair containing A and B, the pair containing A and C, and finally, the pair containing B and C. Those are the only three possibilities, right? If I were to take the pair containing B and A, that wouldn't change anything because, as you know, the order in which we write the member does not matter for a set. And finally, we have the subsets containing three elements, and there's only one, and that's A itself. Right? So if we want to write the set of all subsets of A, notice that now it has 8 members. Right? So when we took a set with 0 members, it had one subset. When we took a set with 1 member, it had 2 subsets. When we took a set with 2 members, it had 4 subsets. Now we take a set with 3 members and it has 8 subsets. And maybe we're onto something here. And yes, we are. In general, if you pick a set with n elements, the number of subsets its power set will contain is 2 to the power n. So if you had a set containing 10 elements, that means you would have 10 to the power 10 subsets, which is, if I'm not wrong, 10,024. I hope that's correct. It should be correct. All right. But now, so far, I've been talking about those sets of subsets as if we're already guaranteed that they exist, right? I've just made a list and I've written things out. But is there anything in our axioms of set theory that guarantees that those sets of subsets exist? And in fact, no. I mean, there are some particular cases in which the answer is yes. But as a general answer, give me any set and I can give you the set of its subsets. No, we are not guaranteed that those exist in general. So this is why we introduce the power set axiom, which tells us, yes, those sets of subsets exist. So here, for any set S, you give me a set S, and I want to give you a set containing all the subsets of S. Right, so for any set S, there exists another set P such that for all X, if X is a subset of S, then X belongs to P. So that is to say, P contains all the subsets of S. And that's what the power set axiom guarantees to us, that this exists. Okay? So the set P, a bit like when we were introducing the union set axiom, the set that is guaranteed to exist by the axiom is sure going to contain all the subsets of S, but it could contain many other things. Okay, so the next thing that we're going to do is we're going to take our axiom, we're going to apply separation to it, and we're going to define a particular set, which we're going to call the power set, which is going to contain all the subsets of a set, say S, but nothing else. Okay, so let's do that. Definition of power set. Sorry, power set I thought was going to show up here, but it is not. Okay, so we're going to say let S be a set, and let P be one of those sets that's guaranteed to exist by the power set axiom that contains all the subsets of S. Now, the power set is defined by separating this set P that's guaranteed to exist by the axiom, the power set axiom. But the membership condition is going to be that X is a subset of S, and therefore that set here, P parenthesis S parenthesis, that's to be read as a whole as the power set of S. Okay, and that's this definition here. Now, the membership condition is here on the right-hand side. So we get the statement that X is in the power set of S. Sorry, that's a different formatting. It should be. In the notes, I've used that, but I think for those slides, I made a mistake and I used that font. So stay on your guard. That font and that font should be the same. Oh, too bad. Okay, so X is in the power set of S if and only if X is a subset of S. Okay, now based on that, we can introduce two Fichte-style rules that are going to assist us in writing proofs when we're going to have theorems involving power sets. So the first is, well, just the membership condition. That's why I call it MC power set. And the second, again, is just MC power set, but going in the other direction because that's an if and only if, right? So if X is in the power set of S, it follows that X is a subset of S. And on the other hand, if X is a subset of S, it follows that X is in the power set of S. So that goes both ways. Okay, so let's look at a little example that is pushing things just a bit beyond what we saw in those other examples before. Now, P, the power set operator, can be iterated. So sure, we can talk of a set S and forms the power set of S, the set of all subsets of S. But we can also form the power set of the power set of S. What is this? Well, let's look at an example. So here I took a very simple case where S is a pair that contains two objects A and B. And earlier we saw that the set of its subsets is what is here on the right-hand side of the equation. And now we know that this set is what we're going to call the power set of S. Now, what about the power set of the power set of S? Well, that's going to be the set of all subsets of that set here that has 4 elements. So let's look at what that would be. Well, it has how many elements, you think? 16, because the power set of S has 4 elements. So the power set of that set should has 2 to the power 4, which is 16 elements. So at first, I listed all the subsets with 0 members. That's the empty set. There's only one. Then I listed all the subsets of PS that contain 1 element. So I have singleton of the first member, then singleton of the second member, then singleton of the third member, then singleton of the fourth member. Easy breezy, right? And we can see that each of those are in fact subsets of the power set of S. And then we have all the subsets that are going to contain 2 elements of that set that we have here, namely containing the first and the second. Right? So we have a pair containing the first and the second object. Then we have another pair containing the first and the third. Then another pair containing the first and the fourth. Then another pair containing the first and the second, the second and the third, then another one containing the second and the fourth, then finally a sixth pair containing the third and the fourth. And then we have all those subsets that contain 3 of those elements. So here I have the one that contains the first, the second, and the third element of PS. Here I have the one that contains the first, the second, and the fourth element of PS. Then I have the one that contains the first, the third, and the fourth element of PS. And finally, I have the one that contains the second, the third, and the fourth element of PS. So there is, again, 4 sets of 3 members that are subsets of PS. And finally, PS itself, right? PS is, of course, a subset of PS because subset is a reflexive relation. So now we know that there is 16 members listed. We can just count all of them, and that tells us that our list is complete, right? So if I give you a set with 5 elements, which I will not do because it's cruel, okay? But if I gave you a set with 5 elements and asked you to list all of the subsets, well, you would know that there should be 32 members of the power set. Right? So then when you start listing all of them, at the end, just count them to make sure that you didn't forget or miss any of them. Okay? Now, as you see, writing power sets explicitly, extensionally, is quite tedious because there is so many members of those sets and it's really painful. By the way, I'm touching my face, which is fine because I'm already infected with the virus. Okay. And I'm not leaving my house, so I'm not contaminating anybody. But, all right, since those power sets are so hard to, or tedious to deal with extensionally, we normally just deal with them algebraically, or just in terms of their general definition and of the general properties that follow from that. So let's just turn to that right now. So here's the first one. That is very easy, very straightforward, and that will illustrate the deduction rules that I have given you to deal with power sets. So the idea is take any 2 sets A and B if A is a subset of B, it follows that the power set of A is a subset of the power set of B. So I've gone straight to the key part of the proof where we suppose that A is a subset of B, and we try to show that as a result, the power set of A is a subset of the power set of B. And again, we're going to proceed backwards, right? Just like we have always done with our deductions. Now, what do you think we're going to do first, right? Well, we look at our goal, and it's a subset claim, which means that we're going to need to reach a conclusion that states that something is a subset of something else. Now that tells us what we have to do right there, right? So we have to first utilize the definition of subset, and that tells us that for all x, if x is in the power set of A, then x is in the power set of B. If we were to reach that line, then we would reach our goal immediately by the definition of subset. Now, how do we reach that formula here for all x, x is in blah, blah, blah? Well, that's a universal sentence, right? The universal quantifier is the main operator, and that in itself tells us that we're going to reach that second to last formula by doing a universal introduction, which is why I set my sub goal as some object A, an arbitrary object, is in the power set of A, and it will follow, hopefully, that's our sub goal. We're going to try to show that A is in the power set of B. And of course, the main operator of that line is a conditional. So that means we're going to proceed by conditional proof. So on the first line, we write A is in the power set of A. And on the last line, A is in the power set of B. Easy. All right? And now again, we're going to keep thinking backwards. You know that it's the trick to become good at writing proofs. We always want to work backwards. So we look at this sentence, A is in the power set of B, and we ask ourselves, how am I going to reach that? Well, we have a sentence involving a claim that something is in the power set of something else. So our first reaction should be, well, let me look into the rule that applies to the membership condition of a power set. And that's going to tell us that to reach the conclusion that A is in the power set of B, it must be the case, so we're going to set that as our sub-goal, that A is a subset of B. And then we're going to ask ourselves, well, how are we going to reach that, right? How are we going to reach that? Well, maybe we can look at the membership condition as it applies to our supposition A is in the power set of big A. And that's going to tell us A is a subset of A. Directly, that's the membership condition, okay? So what do we do next? Well, we see something. We should see something because we've worked so hard on proving those things. Small a is a subset of A. A is a subset of B on line 1. Transitivity of subsets tells us that as a result, it follows directly that A is a subset of B. Beautiful, isn't it? Very simple theorem. Now, here I've presented the proof as a Fitch diagram. As you know, for the remaining part of the semester, I just want to see proofs in prose, like the one that they write in mathematics textbook and the sort of stuff that they would ask you to provide in a mathematics assignment. And of course, it's not just in math, right? In all disciplines, be it computer science, philosophy, linguistics, economics, engineering, physics, whatnot. Any discipline that uses math when they write proofs, that's a proof in prose. So then the challenge is to convert that Fitch diagram into a proof in prose. The proof in prose is written in the notes, so I'm not going to go over that, but have a look at that and make sure that you understand how I've converted that Fitch diagram proof into a proof in prose. If you can do the Fitch diagram, your proof in prose is going to be impeccable. And that's what we want. That's what we're trying to learn to do. Okay, so I hope that one is a first easy theorem to get started. Following that theorem in the notes, there are two exercises that are relatively straightforward. In fact, they are just applications of that theorem that we just looked at. Again, that theorem says if A is a subset of B, then the power set of A is a subset of the power set of E. So let's look at those applications. The first one says if A is in a collection of set C, then the power set of A is a subset of the power set of the union of the collection. Now, it might look a little bit intimidating at first, but there are a few things that we have shown before. In fact, I don't know if it was an assignment question, but it's definitely something that you have looked at in the 5th chapter. Now, if A is in a collection of sets, it follows that A is a subset of the union of the collection. Why? Because the union of the collection contains every single object that is in every single set in the collection. So, of course, all the members of A are going to be members of the union of the collection. So A is a subset of the union of the collection, and by virtue of the theorem, which we've just proved on the last slide, it follows that the power set of A is a subset of the power set of the union of the collection. So that's the first one. And there's another one, which is based on the same idea. One of the things we discussed last time, or anyway, in the previous set of notes, if A is part of the collection, then the intersection of the collection is going to be a subset of A, right? Because the intersection of the collection contains those objects that are in every single set in the collection. So of course, all of them are going to be part of A. It has to, right? So since A is since the intersection of the collection is a subset of A, whenever A is in the collection, it follows that the power set of the intersection is a subset of the power set of A member of the collection. Right? So that's fairly straightforward application of that theorem that we saw on the previous slide. Okay, so let's look at another theorem involving subsets. And again, those look a little bit intimidating at first, but if you proceed with this Fitch approach that we have developed, none of that should stop you. So now we're going to start with any collection of set C and any set A whatsoever. And if A is in the collection, then it follows that the power set of A is a member of the power set of the power set of the union of the collection. What is this? Well, so what this theorem is saying is the following, basically. Imagine you have a collection of sets. It contains many sets. A is going to be one of them under our assumption here. Now, is there a set that contains the power set of every set in the collection C, including A? And the answer is yes, there is one, and that is this monstrosity, the power set of the union of C. What is this? It's huge, it's huge. So we're not going to even try writing out all the members of that. That would just be too annoying. But the beauty is that doing a deduction, we can just see fairly easily that it is true. So again, we have our supposition, A is in the collection, and we have our sub-goal here, the power set of, no, not our sub-goal, our final goal. The power set of A is in the power set of the union set of C. That's a mouthful to say. But what's important to notice here is that we have something being a member of a power set. So that tells us, let me use my membership condition for power set. And that means I'm going to reach my main goal by first obtaining the line, the power set of A is a subset of the power set of union C. That was one of the exercises on the last slide, but just to help a little bit, I'm going to go through with it. So that's our sub-goal here. And well, it's saying that something is a subset of another thing. And now we know how to do that, right? I'm skipping the universal generalization or universal introduction, as well as the use of the definition of subset, and putting all of that in one go. So I first suppose that an arbitrary element is in the power set of A, and then I'm going to try to show that as a result, that arbitrary element is in the power set of the union of the collection. That's a big thing to say. But again, our sub-goal here says that something is in some power set, right? So that tells us, why don't we use the membership condition again, right? So if I knew that A is a subset of the union of the collection, I'd get my sub-goal immediately, and I would be so pleased with myself. So how can I do that? Well, I could open immediately a subproof, right? I could do that. But instead, I'm going to apply my membership condition to my supposition as well, just because it's easier to work with subsets. And that tells me that A is a subset of the set A. And there's a theorem in the notes that tells you that if something is a subset of a member of a collection, then that set has to be a subset of the union of the collection. Okay, that's one of the theorems that we proved in chapter 5. So of course you can fill in the gaps again and open a subproof and actually show it. But if you do remember having seen it in chapter 5, you can just say, hey, we've already proved that in chapter 5, and we're good to go, and that completes the proof. Okay, so that would be cool. I hope that makes some sense. Okay, this is in fact on the easier side of the proofs that you're going to have to do involving power sets. As you were going to see, there's going to be some that are a lot more involved, a lot heavier. Okay, so let's start with something that is not yet too heavy, which is how do power sets interact with finite unions and intersection? The way in which power sets interact with those other set operators, namely finite union and intersection, that's an example of what I was talking about earlier in terms of the algebraic properties of power sets. So let's first just look at an example, and we're going to see if we can generalize from that. So here I'm taking two sets, A and B, that contain 3 elements each. And as you see, there is 2 overlapping elements, right? So the intersection of A and B contains B and C. Okay, so now we have a set with 2 elements. What if we take the power set of that set with 2 elements, taking the power set of the intersection? Well, A intersection B contains 2 objects, so the power set is going to contain 4, namely the empty set, singleton B, singleton C, and the pair BC. Now, to look at the intersection of the 2 power set, let's look at the the intersection of the power set of A and the power set of B. Let's look at them separately. Now, A contains 3 objects, which means its power set contains 8 objects, which are listed here. The power set of B is also going to contain 8 objects because B contains 3 objects. They are listed here. And then we look for the intersection of those 2 sets. So the empty set is in both, ergo it's in the intersection. Okay. Singleton B is in both, ergo it is in the intersection here. Singleton C is in both, so again it's in the intersection set. And finally, the pair BC is in both, and therefore it ends up in the intersection. So compare line number 1 here with line number 4, and we see, oh my God, those 2 sets have exactly the same numbers, the same members. So that means that the intersection of the power set equals the power set of the intersection. Isn't that beautiful? So that means that if you first take the intersection and then the power set, or first take the power set and then take the intersection, doesn't make a difference. Isn't that beautiful? I think it is. Now, is this just an accident of this particular example? The answer is no, it is a general fact. In fact, there are two theorems that are relevant here. The first says the intersection of power sets is the power set of the intersection. That's the first part. However, for unions, this is not true in general, right? So it is true that the union of the power sets is a subset of the power set of the union, but the other way around doesn't work. And one of the exercises in the notes asks you to find a counterexample to part number 2 of that theorem to show that the power set of A union B is not in fact a subset of power set A union power set B. So we're going to prove part number 1, and 2 is going to be left as an exercise. So we want to show that this set equals this set. Now, as we saw, thanks to the anti-symmetry of subsets, it's often a good strategy to break down a problem about identity of sets into two parts, two directions, where first we show that the first set is a subset of the second, and then that the second is a subset of the first, and we infer from that that they must be equal. So let's start with the beginning. Power set of A intersection power set of B is a subset of the power set of the intersection. That's a subset claim, which means we're going to do a conditional proof, assuming that some arbitrary object is in the intersection of the power sets, and trying to reach the conclusion that as a result, that arbitrary object is in the power set of the intersection. What do I start with? Think about it. Yes, it is what you were thinking. I'm going to use the membership condition rule for power sets. Right? So how do I reach my conclusion that A is in the power set of the intersection? Well, I first derive that A is a subset of the intersection. Easy breezy, right? Now, I could just open a subproof, okay, and work from there. But again, I'm just going to apply my membership condition to my supposition because it's often going to be required anyway. So that says A is in some intersection. The membership condition for intersection tells me, therefore, that A is in the left-hand side of the intersection, and A is in the right-hand side of the intersection as well. And applying the membership condition, because again, here we have claims about things that are in power sets, that tells me that A is a subset of A. Sorry, a little bit more than I was thinking showed up. So A is a subset, the arbitrary object is a subset of A, and the arbitrary object is a subset of B. Now, that means that the following conditional is true, right? If some object is in our arbitrary set, because now we think it's going to be a subset since we have a subset claim, right? The left-hand side of a subset claim has to be a set, right? So if something is in our arbitrary object A, well, that means that that arbitrary object X has to be in A and in B as well. It has to be in both. And that tells us that A is a subset of the intersection. Okay, so that completes the first part of the proof. And then we turn things around. We try to show that the power set of the intersection is a subset of the intersection of the power sets. So again, I have a subset claim made here. So I'm going to suppose an arbitrary object is in the left-hand side, the power set of A intersection B. And I'll try to derive the fact that this arbitrary object is in the power set of A intersection the power set of B. Isn't that terrible? Well, not so bad, not so bad. So let's just use our membership condition. A is in some intersection, which means it's in the first part of the intersection and in the second part of the intersection. And again, that means A is a subset of A. The arbitrary object is a subset of A, and the arbitrary object is a subset of B. Now, our supposition here tells us that A is a subset of A and B, and that since A and B is a subset of A and B is a subset of B, we've shown that in chapter 5, it directly follows that we have the rest of the proof. All right. Whew, isn't that beautiful? Now, between line 9 and 10, you could have repeated something like line 4, right? There's nothing wrong with that. Here, I thought it was clear enough if we just leave it like that. Good. So I consider those to be relatively straightforward. Okay, so power sets are a little bit trickier than other parts of set theory that we looked at so far. But to the extent that power sets go, that's among the easier theorems. Okay, so now we move to something that is more abstract, therefore more difficult, and in my experience, students do find that more difficult. So we're going to try to take it step by step, really to try to capture this whole idea. But we want to look at how the power set interacts, not just with binary union and binary intersection like we just did, but now we want to see how it interacts with arbitrary unions and arbitrary intersection. So we have the big operator that says arbitrary union. And it's bigger than the small one for binary union. So we've seen before that if we have the union of a collection and take its power set and take the power set of this, that monstrosity is going to contain the power set of all the members of the collection C. You might be thinking, we saw that, right? So let's go back a little bit. Sorry to skip through the slides. And that's what we showed right here, right? Take any collection and any set in that collection. The power set of that set is going to be in that monstrosity. So that means that monstrosity contains the power set of every set in the collection. So now we go back. We saw that, but we also saw that this monstrosity sure does contain all the power sets of all the sets in the collection, but it can contain more stuff, right? So now what we're going to do is we're going to try to form a set that contains all the power sets of the sets in the collection and nothing else. So we're going to take that monstrosity that contains all those power sets, and we're going to apply separation to it. Right? So let's look at what the condition here says. There exists a set, that set's in the collection, and X is in the power set of S. So that part here is saying what? Is saying X is the power set of some set in the collection, right? So that means that our set E here contains all the power sets of the elements of the collection C, and it contains only those things, because in order to be in the set E, you have to be equal to the power set of some set in the collection. Okay, so that's scary. Okay, that's a huge sequence of symbols that looks insane a little bit, but focus just on the membership condition, and it's telling you E is the set that contains the power set of everything in the collection C. Okay, now again, just that right-hand side of the colon is going to be important for us. So I wanted to mention that we're applying separation to that monstrosity, but now that we have the membership condition, right, we don't need to remember much about that at all. Now, the reason why we're introducing that is because, well, there's a sort of notation that is very common in mathematics. You take the union for each set in the collection, you take the union of all those power sets, right? So in order to make sense of that notation, you need to think of having a collection of all the subsets. You have you have a collection of the power set of every set in the collection C. which is mentioned here. That set, that collection, as we saw, is E, right? So to take the union of all those power sets is really to take the union of E just in the way that we have defined earlier, okay? So that's just going to be the same thing. We're going to see a little bit how it comes together in proofs. And again, to take the intersection of all the power sets of the members of the collection is to take the intersection of the collection E, which contains all those power sets. Now, by means of that, we can show the algebraic property that I promised to you that we would look at, which is that if you take the intersection of power sets, that's the same as taking the power sets of an intersection, right? So the order of the two operators doesn't matter. Now for subsets, it does matter, okay? It does matter a little bit. In fact, if you take the union and then the power set, that's going to be a subset of what you get if you take the power set and then the union. And the other direction does not work, okay? So since for the binary case, we proved part 1, now we're going to prove part 2, which is going to give you a flavor of the other kind of proof that's involved here. All right, so should we look at a Fitch diagram? Again, the proof in prose is given in the notes, so let's work through the Fitch diagram to try to understand how to construct those proofs. And as you see, it's 19 lines, so it's a pretty big monstrosity. And do you think there's any chance in the world that you're going to find that if you don't work backwards from the conclusion? There's not a single chance, all right? So you have to work backwards. So here I wrote my theorem on line 19. That's a claim saying that something is a subset of that other thing. We don't have to think yet about what those things are. We see a subset claim, and that tells us some arbitrary object is in that thing, implies that this arbitrary object is in that other thing. Now, why did I use a capital A as opposed to a lowercase a? It doesn't matter, right? It really does not matter. But I know that power sets are always collections of sets. That's something that emerged from the examples that we looked at. So since I know that the power set of anything is a collection of sets, I know that its members are going to be sets themselves, which is why I use the capital letter here. But it's just a small thing, okay? So now we have 18, which is our sub-goal. That's a conditional sentence. So I'm going to set up a conditional proof. That's just blindly mechanical. We've done that so many times now that it's easy, right? I'm sorry, there's a parenthesis missing on line number 1. So what are we going to do next? Well, we're just going to use our membership condition for a power set. That tells us that A is in the power set of the union of a collection. Oh, sorry, I used the notational equivalence between those two things. And then I used the membership condition, which is A is a subset of the union of a collection. So that's not so bad, right? Now, I might be tempted to set up another conditional proof immediately. And that wouldn't be the end of the world. Definitely not the end of the world. However, you'll remember that when we do proofs involving Fitch diagrams, we always want to do proofs by case first if we can, or existential elimination first if we can, right? And here we have a situation where line 1 hides an existential sentence. Because what's the membership condition for that thing here? Well, just by definition, we define that expression with the extra parenthesis missing as being A is in the union of the collection E. And to be in a union set, means that there is a set B such that A is in B, and furthermore, B is in the collection. That's just the membership condition of arbitrary unions. So as you see, our line number 1 was hiding an existential sentence. And now that we have that, it's going to be fairly straightforward for us to say, all right, let's just do an existential elimination. So here I do an existential elimination with B. I use a new letter that I haven't used before. I choose D here. So I say A is in D, and furthermore, D is in E, that monstrous set that we saw. Okay. Now, if you remember the membership condition for the set E, it also included an existential sentence. Okay, so I'm going to again apply conjunction elimination to get line number 6, which is the second disjunct in line 4. And I'm going to notice that this hides an existential sentence. So there exists an F. I could have used S, it doesn't matter. I just take the letters in order in which they come, right? So there exists an F such that F is in the collection and D is the power set of F. That's saying D is the power set of some member in the collection C. That's what it says to be in the set E. So what am I going to do next? I'm going to have to do another existential elimination, right? So I take the next letter that hasn't been used yet, and that tells me G is in the collection C, and D is equal to the power set of G. Beautiful stuff, isn't it? Now try to get to that point without thinking backwards and using the rules of thumb that we've examined in this course. Now this is a fairly hard proof if you don't have a method, but this is why I'm very confident in the method that I'm teaching to you in this course, because so far there hasn't been anything that's rocket science. It's more or less just about following the principles that we saw always apply. And now we just need to go from line 8 to that thing. Now notice that we had a sub-goal here. We just keep carrying it as is within our sub-proofs for the existential elimination, just like we did before in our other proofs in predicate logic. Nothing has changed. All right, so again, we could open a new sub-proof to do to get to that conclusion, right? Saying some arbitrary object is in A implies some arbitrary object is in the union set of the collection. Nothing wrong with that. But also, I mean, we have some other ideas that we might be able to deploy. So I want to work with some of my sentences here that I haven't used. Again, there would be nothing wrong with going and working with that. But in that little part here that we have to do, there is actually one idea that you should spot, which isn't an automatic idea, right? You should think a little bit about stuff that we have discussed before involving union sets. And in fact, we've used that fact today already. So let's just look at what we have. So first of all, the second conjunct on line 8 is an identity sentence, right? And now we have a number of things that come together, right? We have the D equals the power set of G. And now we look at those other things that involve D, right? And we have A is a member of D. Line 6, we've used it already, so we can forget about it. But line 5, we haven't really used yet, right? So now we know A is in D, D is in the power set of G. So that's telling us that A is in the power set of G. That's just substitution of identicals. And then the membership condition for line 10 tells us A is a subset of G, right? And then we should see something very cool, right? So we have again on line 8, On line 8, let's apply conjunction elimination. We have G is a member of the collection. And now we've seen that idea that I was pointing out before already. G is a set in the collection. Whoops. G is a set in the collection. A is a subset of G. It follows automatically, that's theorem 5.8, that A must be a subset of the union of the collection. All right, so remembering theorem 5.8 is quite important in those proofs. Again, there are other ways of doing it, but that one is just the easiest one. So I invite you to stop again, think about theorem 5.8. It's going to be very convenient very often. And then we just complete the proof in the way that we said when we were working backwards. And that gives us that big thing, okay? So that's not an easy one, definitely not an easy one, but I hope that you see that there's a method in the madness, and that once you have that method, the madness becomes kind of beautiful when you think of it, right? So now you have a Fitch diagram and you want to rewrite that in prose. So in the notes, there's a prose version of it. Try to think of the way in which I mapped this Fitch diagram onto the words. Of course, I've simplified a little bit the English. I've skipped a few more steps because it's hard to follow every step like that in English. Otherwise, if we write all the steps in English, we start missing the forest for the tree. So skipping steps is an important part of communicating clearly. So you're going to see how I've done that. But I'm not going to do that here. There are a few other properties of power sets that kind of follow from that idea that we just looked at. Now, I mentioned that before. If you take a set E, the power set of E is always a collection of sets, right? So since the power set of E is itself a collection of sets, that means we can look at what happens if we take the intersection and the union of that collection, right? So that's what we have here there are a few exercises in the notes that exploit this idea. So take any set E. What happens if you take the intersection of the power set of E? Well, here it says the empty set, and you might be like, why would that be the empty set? Why would that be the empty set? Well, there is one set. Well, in fact, there are two sets that are always in the power sets, right? So if you take any set E, there are two things that are always subsets of E. E itself and the empty set. Now, the empty set is a subset of everything. So that means the empty set is a member of the power set. So it's one set in the collection. And E is also a set in the collection. Now, if you take the intersection of a collection that contains the empty set, the result is the empty set. We looked at that one in the previous chapter. In fact, it might be an assignment question. I don't remember. But also, take any set. Since, again, the power set contains E itself, that means the union will be E. It's going to contain everything. Isn't that cool? I think it is. Yeah, so another application of the theorem that we just saw is that E is a subset of the power set of the union. And that's just a subset. They are not equal. So you can try to find a simple case. Take E maybe to be just a pair, right? A pair containing two objects. And try to find a counterexample to what's happening in the reverse order. So have a look at that. Those are just fun little things to play with. Now, we're going to look at one last application of power sets, which is really important. Because at the end of chapter 5, we proved a version of the De Morgan laws for binary union and binary intersection and relative complement. In fact, I'm pretty sure one of those is in your assignment, what, 8, 7, 8, yes. And we didn't do that for arbitrary unions and arbitrary intersections. And you might be wondering, why didn't we do that? Isn't that something that Nick overlooked? And the idea is that no, I didn't overlook it. In order to get to that theorem, we in fact needed the power set axiom, which is why it's been postponed up to that point. Now, I should warn you, that part has proved to be difficult in the past for a lot of students. So you're warned. We're again going to try to take it slowly and work with our Fitch diagrams and use our sort of mechanical, methodical approach and try to figure out the proofs. So let's start going. So we're going to take a set E and some collection of sets, right? And the collection of sets C in question is going to be as follows, right? So we know the power set of E is a collection of sets. So it contains a bunch of things. Among the things it contains, there's the empty set, there's E itself, and depending on what E is, there's going to be other things, or not, depending on what E is. Now, C here is, we think of C as containing some of the subsets of E, maybe some, right? It could be an empty collection, but it's going to contain some of the idea is going to contain some of the subsets of E, but maybe not all of them, right? So it's not the full power set, it's a part of the power set. So here's what we want to do with that set E and that collection of subsets of E. So with that collection of subsets, we want to form a new collection of sets, and we're going to call it D, next letter in the alphabet. And that collection D is going to be as follows. So if X, that is to say, X here is going to be a subset of E, if X is in the collection C, right? So if X is one of those subsets that we decided to keep in the collection C, then we'll put the complement of X in the collection D. Right? So for every subset of E that's in C, we're going to put the complement of that subset in D. And the complement here is going to be taken relative to E. So X bar, the complement of X, equals E minus X. All right? So in this way, we have the following set that we can define. D is the set that contains sets. So it's D is a collection of sets. It contains sets which are subsets of E. Okay? But the subsets of E it contains are precisely the complement of the subsets that C contains. Isn't that beautiful? I think it is beautiful. It's a very cute idea, right? So D is a collection of sets, namely the collection that contains the complement of all the subsets that are contained in C. All of those things are mouthfuls. Huh? When the word set occurs like 5 or 6 times in a sentence, you're like, whoa. Well, you know, it does take time to assimilate all of that. It's normal, you know, it's normal if you're struggling a little bit. You know, those things have to percolate. That takes time. But what we're trying to get here is have a first introduction to them, and we have a method to study the properties of those things, right? And that's a method that is fairly tight, fairly straightforward to follow. So, you know, next time maybe you take a course in linguistics and you do formal semantics, and it's all using set theory and things like that. And you see that there's going to be mappings. We don't know what a mapping yet is technically. We're going to get to it soon, right? We're going to have mappings from a set to the power set of the power set of that set. That's very common in formal semantics, as you see it in linguistics, right? And then you're going to be able to come back, look at those notes. I invite you to download them and keep a copy. And you're going to have that method that we've developed, and you're going to be able to reuse that method in order to understand all those things once again, right? So, I mean, I teach that stuff. I don't remember all those proofs and all those facts. I remember some of them, obviously, but what's the important part here is the method to inquire about those things, and if that method is the thing that is going to stick with us. It allows you to structure your thoughts, to think about very abstract topics, right? So again, all those things are a little bit heavy, but in a way they are just a more challenging context to further develop that method of inquiry that we've been developing here. Okay, so now we have that set D, and that set D is a collection of sets. What sets are in that collection? The complement of the sets that are in C. All right, so let's look at an example. Just try to get a little bit more concreteness. Concreteness, is that a word? Anyway, a bit more concreteness. So we're going to take the set E containing 3 elements. So if we think about the power set of E, how many elements does it contain? 8. E has 8 different subsets. So what are we going to do next? Well, we're going to look at some of those subsets. We want a collection C of subsets of E. Maybe we're going to pick 1, maybe 0, maybe 2, maybe 3. Maybe we're going to pick 8 of them, right? But the idea is that we just want a collection that contains some of those 8 subsets. Here I was trying to say how many different collections of subsets of the power set of E are there? Well, that's the same as the power set of the power set of E, so there would be 256 different collections of subsets that we could look at. Of course, we're not going to look at all of them. Let's consider one of them, namely the collection that contains the empty set, the pair containing A and B, and singleton A. Okay, so C is a collection containing 3 subsets of E, just that. And then we take them one by one. Take the complement of the first, that's E itself, because we take the complement relative to E. Take the complement of the pair that contains AB. What is it going to be? Well, that's going to be the singleton C, right? Which object is not in the pair AB? C, easy. And what is the complement of singleton A? Well, that's going to be the pair containing B and C. So then the set D, which contains the complement of all those sets that are in C, is going to contain E right here, singleton C right here, and the pair containing B and C right here. So myself, when I write those sets of sets, I like to start with the sets that contain the fewer members and move to the set that contains the most members. Of course, the order doesn't matter, but it just helps me to keep things straight in my mind. All right, so that's one example of how we generate a set D from a set C. We have a collection of sets, and we generate a new collection of sets, each whose members are each the complement of one of those subsets that we have here. So that's just a concrete example of what it looks like. But with that set D, we are now in a position to define what it means to take the union of the complement of all the sets in the collection. That's going to be taking the union of that set D that we just defined. Similarly, taking the intersection of the complements is just going to be taking the intersection of that set D. And this is what we need to even formulate our generalized De Morgan laws. So the complement of a union is the intersection of the complements. The complements of the intersection is the union of the complements. So that should have a sort of family resemblance with the De Morgan laws that you examined in this week's assignment, last week's assignment, and the notes for last week. So what should we prove? I don't remember which one I picked. All right, the first direction of one. So we're going to show that this set here is a subset of this set here. And we're going to do it with a Fitch diagram. Oh my God, look at that. It's so big. It's so big. Oh, it's going to be a monstrosity again. Well, we're just going to use our method. We're going to stay calm and we're going to proceed step by step. So here's our conclusion. That set here is a subset of that set here. By the way, sometimes here you see that the X in C is written underneath the symbol for the arbitrary union. Often to use less vertical space, it's used here on the side as an index, as a subscript. That's the same thing. It's just a typesetting convention, which is fairly common in mathematics, but you may not have seen it before. All right, so we have this thing that we want to show. So again, here I'm writing it explicitly. We use the definition of subset that tells us prove a universal conditional. And then to get to that universal conditional, we're going to get a conditional involving an arbitrary element, and we're going to do a universal introduction. Now, in order to get to that line, what are we going to do? Please all say it together. We are going to do a conditional proof. Hallelujah. All right, so we suppose this arbitrary element is in that thing, right? At this point, I haven't even thought about what that thing is. Don't think too much. Thinking is hard. We get good at doing things when we learn how to do them without thinking, in a way, right? So, or don't think too early, right? Why doing thinking today if you can do that thinking tomorrow? Those are words of wisdom. All right, so that's what we suppose, and we want to get to the claim that the arbitrary element is in that other thing that I haven't thought about yet. I just copied what was written there. But now I'm going to think a little bit. I have that symbol here, that series of symbol here, which we just defined on last slide, right? So it's telling us that A is in the intersection of that set D. And then I think about, A, what is it to be a member of an intersection set? Well, my membership condition tells me for all T, where T is just some variable, for all T, if T is in the collection, then A is in T. That's a universal sentence. How am I going to reach it? I'm going to do a universal introduction. So I take some arbitrary set S. If this arbitrary object is in D, then A is in that arbitrary object. And how am I going to do that? Well, I'm going to do a conditional proof. But first, I just wanted to apply the obvious to my supposition as well. So A is in the complement of the union means A is, I just replaced that notation by this equivalent notation. And then A is in the complement of that thing means A is not in that thing. Now that's the membership condition for the complement. And then let's go back to my subgoal here, which is a conditional, and I'm just going to suppose the antecedent and try to reach the consequent. Okay, so what are we going to do here? So far, we haven't put too much thought, right? We mostly went on the cruise control. So what are we going to do now? 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 We think. We try to come up with something. I don't know. What are we going to do here? I don't know what we're going to do here. I don't have any idea. So what do we do when we don't have any idea? What do we do when we don't have any idea? We saw that when we were doing deductions in predicate logic. and in sentential logic. When we don't have any idea, we use the no idea rule, which is prove by contradiction. Oh, apparently I did have an idea. I'm so sorry. I did have an idea. But we're going to get to not having an idea. Yes, of course, we have an idea because S is a member of D. I can use the membership condition for being in the set D, obviously. Sorry. And then we just go back to last slide or to the notes. Look at the membership condition for the set D. It says that S is a member of the power set of E. And furthermore, the complement of S is in C. Why? Because D contains the complement of all those things that are in C. Right, so that's our membership condition. And then we can, of course, just do a wedge elimination. So the complement of S is in C. And I think that's where I like, okay, I did everything that appears obvious. I've applied all my membership conditions. I've applied my definitions. And really, I don't really have much of an idea. So that's when I'm going to try to do my proof by contradiction. So I suppose A is not in S, and I try to get a contradiction from it. Now, in terms of having ideas for what am I going to get for my contradiction, right? That's always the mystery. It's a bit like magic when we do proofs by contradiction. What is that thing that we're trying to get in order to get a contradiction, right? Well, if you look at line 3, I haven't really used that line yet, right? So maybe I could try to contradict it and try to show that A is in the union set of C. Seems like a decent idea, right? So maybe we can do that. Right, so that supposition A is not in S, that tells me that A is in the complement of S, right? That's the membership condition for complements. And now I have something cool that appears. A is a member of the complement of S, and the complement of S is in C. Why don't I put those two together? And that looks awfully like what I need to be in the union of that collection. Let's do a little existential generalization on that symbol, complement of S. Right, that's a set like any other. I can do an existential introduction on it. And that tells me there exists a T, A is in T, and T is in the collection. So A is a member of the union of the collection, which contradicts line number 3. Ha! Isn't that amazing? How did I think of that? Well, that was not so hard when you proceed systematically. And that's why we were doing all those repetitions of doing proofs in sentential logic and predicate logic, because it was about developing those strategic thoughts that now come into play when we are trying to do those proofs in set theory. Right, so everything else follows, and that completes the proof. Wow. All right, you must be exhausted. I'm certainly a little bit tired, so we're going to put an end to that video. And I'm going to do a second video maybe tonight, probably tomorrow, involving the rest of the notes that I have distributed to you for this week. So we're going to start talking about ordered pairs. We're going to start talking about Cartesian products, and we're going to start talking about the extensional characterization of relations. And in particular, we're going to look a little bit into equivalence relations. So in what's going to come next, the idea of the Cartesian product and sets of ordered pairs is going to be the most important thing. In this course, I'm not going to have much I'm going to talk a little bit about equivalence relations, but it's not a core part of where we're going, so I'm going to go over that fairly quickly, okay? But for those of you, especially those of you in maths or in comp sci, the idea of an equivalence class is important, so I'm still going to mention it, even if it's not a core part of where we're going to go in this course. All right, so have an excellent time, and yeah, so see you in the next video. Bye-bye.